DSC experiment. Okay. We have 2 cells. Okay. We have temperature probes in them. We have heating elements. Okay, so we can control both the heating rate of these 2 cells, and we can also monitor the temperature of them. In one of them, we have our protein in a buffer solution, most likely just water. So we have protein and water, and then in our other cell, we just have the water part, just the buffer part, none of the protein, none of our sample of interest. You can do DSC with lots of materials. It doesn't have to be biological materials, so you could just put, for example, you have air in one, and you have a plastic cup in the other, and you melt it. You want to measure the melting temperature of the plastic. That's the kind of DSC I did in material science, was, of course, I think we put a coffee bean in there. I think we put some hair in there, which hair is keratin, so I mean, that's kind of a biological molecule, yeah. So yeah, we just burned a bunch of stuff in the DSC, which was, it's cooler now than when I was doing it for credit. So anyways, this is our basic structure of the differential scanning calorimeter, okay? And we also saw this curve here. So when we're talking about proteins in buffer versus just the buffer by itself as our reference cell, we were looking at what's the change in heat capacity of our protein as we heat it up. And we talked about before, here we're just heating the whole solution. We're just changing kinetic energy. Things are moving faster as we put heat in. And we talked about this. This was all those potential energy modes. We're getting it to vibrate. We're getting the secondary interactions to start breaking apart and unfolding it. And eventually, once it's totally unfolded, we go back on our merry way. And just so everyone is maybe clear, our book really only talks about heat capacity, okay? Or the heat transfer, delta H or Q, at constant pressure needed to raise the temperature of the system by 1 degree. But heat capacity is something called specific heat times mass, okay? So the amount of protein you have matters. You can control that though in your experiment, right? You can control how much you put in. So just, I think there were some people who were using specific heat and heat capacity interchangeably, and this is the difference. So let's try drawing some stuff. Not gonna draw on the board, it's too risky. Yes, no. The light's on. It's not going to click the whole time again, is it? No, I'm not looking at it. It drives me nuts. Okay. So, what is today? 3:20. That's good. So for DSC, we have our reference pan. Can you pull the papers in? Yeah. There's like an art to making sure you can see it. So we have our reference pan, which will just be our solution. And then we have our sample pan that we care about, right? And this has protein that we're interested in, plus our solution. And like I said, this is usually just going to be water for our case. So kind of the first thing we do with DSC is we're going to start heating both of these. We're going to start heating both of them at the same heat flow rate. Meaning change in heat over change in time. Okay, heating flow rate. This is going to be in watts or joules per second, right? Joules is our unit for heat, second is our time here. And the other thing we're going to do kind of at the same time is we're going to do a temperature scan. So we're going to do a temperature scan. We're going to look at the change in temperature with the change in time. All right. These are things we can sort of set on our DSC instrument. Okay. And so then the third thing that the instrument wants to do is it's going to make sure that we keep both cells at the same temperature. And do you think that it, as you heat both of these, which one is it harder to raise the temperature of at our constant dt over d little t at the same temperature rate? The sample one, right? There's something in there. Okay, so the sample's going to take more heat. Will take more heat to be at the same temp. Okay, so we can draw first, let's draw a time versus temperature profile. So what we want to do, our reference sample, we're going to heat linearly. This is our reference pan, and we're just going to heat it linearly. And our sample will start that way, and eventually you would get some sort of dip, something that looks like this maybe in your scan. This is the sample, the protein. And so what we want to do is kind of force this curve linear through power compensation. And which of these things on here was in units of power?
The dq/dt.
The dq/dt. The heat flow rate is in a unit of power. This is in our wattage. So we'll go ahead and control this to force a linear increase in temperature. Okay. So if we plotted then versus time, let's say this is change in heat flow, and it's actually usually going to be in milliwatts. Okay. So basically, we could measure a change in heat flow. Okay. This would be equal to what's the heat flow that we need to supply to the sample minus the heat flow that we need to supply to the reference pan. Okay, there's some difference here. We have to put in more heat in order to keep the linear temperature increase. Okay, so if we want to measure this change in the heat flow that we're doing between our sample and our reference, let this be 0. This is more heat flow has to go in. Let this be the negative sign. So as we move along, we're kind of at 0. They're doing the exact same thing, and then eventually we're going to get a peak that looks kind of like this. Okay. And say this is now hypothetical, we're no longer talking about protein. You could also get a curve that looks something like that. This is an endotherm. It's basically telling us we have to put in more heat in order to maintain that temperature. If you saw something like this on your curve, because remember you can run DSC with a whole mess of materials, it doesn't just have to be proteins. This would be an exotherm. There's some release of heat. We want to put in less heat. Whatever's going on in there, it's releasing heat on its own to raise the temperature. So we're going to pull back. So that could be some type of, any exothermic reaction or combustion reaction. Okay. So the heat capacity in our sample cell, our protein sample, right? Our sample is buffer plus protein, is equal to the heating rate of the sample divided by the temperature scan. So we have dq of our sample over dt. This was our definition of heat capacity. Change in heat with respect to temperature. Okay? And then you could also have the CP of your reference, right? This is just buffer. Looks kind of the same. Heating rate of the reference cell over our temperature scan rate. That's our heat capacity of our buffer only.